Okay, so for part 1 here of homework 7-2. So picking up with question 1 then, they give us a dumbbell-shaped object that's composed of two equal masses. So basically I've got one mass over here, I have a thin rod, and then another mass over here, the same mass. And it does tell us, I believe, yeah, the rod length, the rod is going to be negligible mass, so I'm not worried about the mass of that. The moment of inertia I1 is defined as when it's passing through the axis of rotation through the center of the rod, right? So they've defined I1 when it goes through the center, and they've defined I2 as the axis of rotation being over here. And then they ask us to compare those two. Well, I would hope that most of us probably feel comfortable enough in general just to say that I1 is going to be smaller than I2, and that is in fact the correct answer, right? Option C is going to be the right answer for this. But let's make sure we can kind of comfortably see why using some mathematics if I needed to. All right, so if I was actually calculating I1, well, again, I would do m1 r1 squared plus m2 r2 squared for each of those two masses, right? So I would be, again, mass, which is just m, and then how far away is it from the axis of rotation? Well, it's 1/2 of the length, right? It'd be half of the length away. So I'd have m times half the length squared plus another m times the second mass would also be half the length away. So I'd have that squared as well. So obviously when I square this, I end up with 1/4 ml and then 1/4 ml. So in total, I end up with the two 1/4 adding up to be 1/2 ml squared. Right? So that's what I end up with from the result here for I1. So then for I2, well, let's just say that I chose the left-hand end to be my axis of rotation. Well, then this one wouldn't really cause any type of moment of inertia, right? Because its length, its radius would be 0. But for I2, I would have the full length for this guy. So it would come from just this mass over here, so m1 or m times r1 squared. So again, using that mass, it would be m, and then the r, the length between the axis of rotation and that second mass, would be the full length of the rod, so it would be L squared. So I2 ends up being just a single, right, so 1 ml squared. So then if I compare the two, obviously 1 ml squared is going to be bigger than 1/2 ml squared, and that draws me right back here to the fact that I2 is going to be bigger than I1. So hopefully you were comfortable in general, but if you did want to see the mathematics, there's the math that supports that. So example 2, we've got two rotating systems here. They have the same mass attached to them, which is very important because if it has the same hanging mass, then I know I have the same force of gravity pulling down, and ultimately then I'll have the same torque, right? Since I have the same force of gravity, I'll have the same torque pulling downward on those two systems, right? So they asked me which one's going to rotate faster, right? Which one's going to accelerate quicker. So then if I look at these, the only thing that's different for the system, right, I have two masses m that are identical, and then here I have those two masses, the same two masses, but they're closer to the center of rotation. So really the concept that comes to play here is it's using the fact that torque equals the moment of inertia times my angular acceleration. And again, whichever one accelerates quicker, that's going to be the one that hits the ground first. So since they have the same torque, they had the same force of gravity, same radius, so they have the same torque, right? Then in terms of maximizing the acceleration, right, if I want to get the maximum acceleration, then I want my moment of inertia to be as small as possible. So again, a conceptual example builds off of kind of what we did for question 1, but the smaller the moment of inertia means the masses would be closer to the center. So the one on the right is going to land first because those two masses are concentrated closer to the center, and again that would lead us with a smaller moment of inertia and therefore a higher angular acceleration to balance that out. Question 3 is one I know a lot of students have trouble with. There must be an equal amount of mass on both sides of the center of mass. And so it's somewhat misleading, right? You think the center of mass, it's got to be right in the middle. You have to have an equal amount of mass on both sides. But the easiest counterexample I can give for this, so it is going to be false. And the easiest counterexample I can give would be, let's assume we just have two masses. Let's assume I have a very large mass and a very small mass, right? So where would the center of mass for this system be? Well, I think everybody would agree that the center of mass for the system would be pretty close to the larger mass. But then if I pictured, right, if I say this is the center of mass, how much mass do I have on either side? Well, over here again, clearly I have a ton of mass over here, right? A very large mass over here. Whereas on this side, I don't have anything, don't have anything, don't have anything, and then I have a very, very small mass over here. So I think this, if you thought of it this simply, would pretty definitively say that, no, we don't have to have the same amount of mass on both sides. Right here I have a lot of mass, here I don't have hardly any. So make sure you're considering that when we talk about the center of mass, there are actually two things that come into play. Right? The two things are both the mass but also the position. Right? When I calculate the center of mass, we take mass 1 times its position plus mass 2 times its position. So it's not just the mass that matters, it also matters how far away it is. Right? Both of those factors will impact where the center of mass is. So even if I have a small mass, as long as that mass is very far away, the center of mass is still not necessarily going to be balanced on both sides of the, the masses aren't going to be balanced on both sides of the center of mass. So anyway, like I said, this is one that I know a lot of times students struggle with. Your intuition says, well, it's the center of mass, so we should have the same amount of mass on both sides. But again, because this position element comes into play, there's more to it than that. Okay, so then question 4, if the torque on an object adds up to be 0, which of the following must be true? And quite a few good ones to rule out here. So the force also adds up to be 0. That is not necessarily true, right? If I have a situation where maybe this is the pivot point, right? If I have a force over here and a force over here that are equal in opposite directions, or equal, in magnitude and both pushing upward, they would create a torque that is equal in opposite directions. So the torque would add up to be 0, but the force would very clearly both be going in the same direction. So that one's not true. The object is at rest. That is not necessarily true. The object could be either moving linearly like we just saw here, or the object actually could be accelerating, right? Or not accelerating, could be rotating at a constant velocity, right? So if it was rotating at a constant velocity, the torque would still be 0 because it wouldn't be accelerating. So the object does not have to be at rest. The object cannot be turning. Well, again, same thing really as option B. It could be turning, it just can't be accelerating. The object could be accelerating linearly but not turning. Again, we just said it could be turning, so that one's not right. So then the best option is E. The object could be both turning and accelerating linearly. Okay, it definitely could be turning, we've already talked about that. It could be accelerating linearly like we saw in the first example, but it cannot be accelerating rotationally, right? It can't be turning and picking up speed. So anyway, option E is the best choice on question 4. Okay, so for question 5, I went ahead and wrote down the correct answer. So again, feel free to jump ahead if you got those right and are confident with those. But I will show those worked out if you need them. So notice I did use some mixed numbers there, but you guys probably use decimals. So just make sure your decimals agree with those fractions and you're good. But for part A, hopefully it's not too bad, right? Find the coordinates of the center of mass. So again, for part A, all we really have to do is we've got to find the x position for the center of mass, and we've got to find the y position. Well, to find the x position for the center of mass, I just take m1 x1 plus m2 x2 plus m3 x3 and then plus m4 x4. Right, so sorry, x3 and then m4 x4. Got a little ahead of myself there. But anyway, I'd do that, and then I would divide by the total mass, right, of the system. So the total mass of the system, which would obviously be all of the masses added together. So all I have to do then again is just adding those up. So just be careful in terms of thinking about the x and the y positions, right? If I define this as being 0, if I define A as being the origin, since they told me that it's going through point A here, if I define this as 0, then both A and B would have an x value of 0. So I'm going to think of those as objects 1 and 2. So then the x position for the center of mass, again, both of those would be zeros. Both of those positions would be 0. So then I would have 200 grams, so 0.200 kilograms times 10 centimeters, so 0.10 meters, and then plus another 0.200 kilograms times another 0.10 meters, right? So if I take each of these, they're both 200 kilograms, they're both 10 centimeters from our origin. So as I add those up, and then the total mass of the system, right, adding all of those up together, I get 0.700. And that's where I got my my answer then of 0.057 centimeters there. So that's where I got that answer from. Again, if you round it off, 0.057, I'm sorry, this would be meters because I've converted it. So this would be 0.0571 meters, or 5 5/7 centimeters is again what that would equate to. So anyway, we found our x position of mass, right? You just do the exact same thing for the y position. You do the y position for the center of mass, m1, y1 m2, y2, and so on and so forth, right? And then divide by the total mass of the system. So we do the exact same thing for our y coordinates. Again, this time A and D would both be 0 in terms of their y coordinates. So you would end up those two, which are only 8 centimeters above it. So I'd end up with 0.200 times 0.08 plus, again, 0.200 times 0.08, and then all divided by the total mass of the system, which once again is 0.700. So I've got those measurements, and then that's where obviously when I calculate that, I got my 4 4/7 centimeters. So we get about 0.04 and obviously some change as well, meters, which converts to 4 4/7 centimeters. So I've got those two coordinates for my center of mass, and then that's where my answer for part A came from. So anyway, hopefully finding the center mass at this point in the year isn't anything too tricky. Probably the part that you guys need to look at, if anything, was part B. Find the moment of inertia about an axis that passes through point A and is perpendicular to the page. So really the only thing there, if I'm going about a point going through the axis here at A, right? So this is my axis of rotation. Well, the moment of inertia is just going to come from these three masses, right? Masses 1, 2, and 3, or B, C, and D if you prefer. So I've got those three masses, and then to calculate the moment of inertia, for anything, right? What I'm really doing is I'm finding the sum of each of those masses times its position squared, right? So I'm taking mass B times its position squared plus mass C times its position squared, and then plus mass D times its position squared. Right, so as soon as I identify that, it's just a matter of doing some algebra and some trig as need be to figure out the radiuses and plug in positions. So really not too bad, I hope. But 0.200 kilograms again is the mass. Really, it's the mass for each one of these. The radius to object B would be 0.08 centimeters. And notice I am using my standard units, so I did convert these. Right, so I take that and I square that, and then plus my C would be the one that you have to do a little bit of legwork for, right? We've got to find the distance between the axis of rotation and object C, and it just means I have to do a Pythagorean theorem, right? I have to do 8 squared plus 10 squared, and then this ends up being about 12.8 squared. So again, 12.8 centimeters, which for object C then, so mass of 0.2 kilograms, would then be 0.128 centimeters, converting to meters there, so 0.128 meters squared. And then plus my final one for D, which again is just using the longer distance there, the longer rod, so 0.10 squared. So then when I just calculate all of these, right, I add all of these up, and I end up getting 0.00656 kilograms times meters squared. Okay, so my standard unit for the moment of inertia, kilograms times meters squared. So then I will try to get question 6 in here quickly before the end. They give us a 25 kilogram door. They give us those two distances, the height in centimeters, so I'll convert that, and then the width in, again, centimeters, so I'll convert that. What is the door's moment of inertia of rotation about its hinges, and what is its rotation about a vertical axis 15 centimeters from the edge of the door? Right, so they ask us two of these different ones. Well, for option A, for part A here, I should say, not option A, but for part A, I'm doing the moment of inertia about the hinges, right? And so this is essentially then a rod. It's a thin rod here that's being pivoted around one end, right? So that's what we want to be thinking of this as. So if you look at your information sheet, you've got the moment of inertia for a thin rod pivoted around one end as being 1/3 ml squared, right? So as soon as I identify that, this question becomes pretty easy. It's 1/3 the mass of the door, which is 25, and then the length of the door, which would be obviously the length of the radius here, which is going to be the width of the door. So 0.91 meters squared. So for part A, all I have to do then is calculate those numbers and go from there. So calculating that, I end up getting about 6.90 kilograms times meters squared. Part B, I'll probably have to finish this part, I guess, in the next part of the video. But I'll go ahead and write the answer down here, so if you just want to check that. The final answer I get for part B ends up being 4.0508 kilograms times meters squared. So again, I'll show how I got this in the second part of this homework video, but if you think you got it right and you just want to check your answer, there it is, and hopefully you got it right so you won't have to watch that next part.